That's just, that's, so we're good.
Something went wrong there. You need a root at the end.
I need a root.
Yeah.
You mean like a tuber? Like a okay. So I'm Chris, right? I did abstract and bio. Oh, right, you guys saw that one, right? So this my talk's about me, my favorite subject. Okay, it's not my favorite subject, but I'm quite fond of it. Yeah.
So when was this page originally made?
Let's see. I mean, 2016. So
originally.
On the 5th?
Like the first time.
The first time I came up with an HTML page was when I taught the HTML lecture.
No, this particular
It's the same template. Yeah?
Okay.
It's modified, you know, template changes.
Sure.
Time.
So when was the first
But
time?
it's got to be like 2000, yeah? So this is my old school HTML lecture, yeah?
Which I like.
Yeah, no, I see no reason to change. So I'm not, yeah? I'm trying to do better with pictures, though. This is not a good example. So I'm the professor of AI, so my big research right now is in simulated neurons. So I'm going to give a page on neurons. I'm going to talk about the Human Brain Project, because I got a bit of a grant to work on that, which, you know, not too surprisingly is using simulated neurons. Right? I'm going to talk about natural language processing. I got my doctorate in that, and I do that sort of in the background. Right? What's kind of cool is the work is I can do some stuff with neurons to generate natural language processing. Right? And I'll talk about some other AI, because there's a lot of people here doing AI. Yeah? And I'll talk about what you need to do AI and computer science in general. Yeah? You know, it's all right. I got it.
No,
I'm going to ask him a question. Yeah? Okay. So, do you guys have any questions? You in the back who's talking. Any questions? No? You sure? Yeah. Anything will do.
I know that the man I will believe it.
I'm sorry, I didn't quite catch that. I didn't quite catch the question.
Did I have it?
Do you have any questions? No. Okay. That's what I asked you. So, I'm the professor of artificial intelligence here. You can call me Chris if you want. You can call me Professor Huyck if you want. That's a bit weird, but you're welcome to. I'm from Michigan in the U.S. It's pronounced Michigan with a sh, yeah, like fish. Yeah. The BBC has problems with that, as we've noted.
As we know.
Yeah. I got my BSc in computer science with a minor in math, along with AB, because in arts, they invert them in the United States, so it's AB in reverse. So Bachelor of Arts in History, in 1986 from the University of Michigan. Yeah, so that's how old I am, roughly. I got an MSc a couple years later in computer science, and then I went to work at Microsoft. At Microsoft, I wrote Visual Basic. Right? It wasn't just me. I was one of the team who first came up with Visual Basic. Which is kind of interesting, because we wrote it in C++, but there wasn't a C++ compiler back then. So we had to do it with half compiler. It didn't quite work. When I was there, I also worked on Access, which is the database. They were code complete before I arrived, and it actually wasn't shipped before I left. So there's an engineering question. When do you code complete? It's not when you just got the module names down. Yeah? I actually have to have some code in. What else did I do? I did this really cool stuff on remote procedure call protocols. So if you have a procedure and you want to call something on a different machine, how do you do that? I did some work that was really interesting there on that. If they kept me doing that stuff instead of fixing other people's bugs, I might still be there and a much wealthier man. But probably less interesting. So after my MSc, I went to Microsoft, and I came back to get my PhD, and I did it in natural language parsing. So if you want to read through a sentence and build up the way the sentence works, both its syntax and semantics, that's parsing. I did that in 1994, right? It was a reasonable cognitive model, and my supervisors were up there, and you guys probably don't know them, which is all right. Then I went to the American University in Cairo, which is cool. I used to work on Tahrir Square across from the Egyptian Museum, which was nice. I was there for 2 years.
Is that the one in Mahdi?
Mm-mm. It's now in Mahdi, right? The core of the campus is still downtown. They've moved the CS to Mahdi, but it used to be downtown, which was cool. They were good. They did good work there. And Mahdi's in the suburbs, for those of you who were quasi-interested of that. Yeah. I came to Britain in 1997. I had a postdoc at U of Sheffield with Yorick Wilkes. I worked on the general architecture for text engineering there. I just extended my parser to resolve PP, prepositional phrase attachment ambiguity. Guys know what prepositional phrase attachment ambiguity is?
Pretty much
You know what a prepositional phrase is? You do?
It's where one sentence has several different meanings.
Yeah. The preposition is ambiguous. So how do you attach it? So my classic example of that is I saw the girl with the telescope. What are the two readings for that? Not you.
No, I know.
Okay.
I want to ask something else.
Shoot.
Is anaphora a case of prepositional phrase
No,
attachment, or is it
anaphora is
distinct?
it. Right, that's resolving what the pronoun refers to.
Right.
Yeah. So
Okay.
anaphora is a different thing. Yeah.
Yeah. All right.
You also have to resolve what noun phrases in general refer to. But, yeah. So what were the two interpretations?
You could see the girl and she has a telescope.
Yep.
Or you're using a telescope to see the girl.
So it's ambiguous. There are two interpretations, right? When you guys read that, did you see? You guys didn't read it, did you? You did. Yeah. When you read it, what's the interpretation you come up with? Almost everyone. No one even notices it, right? You normally just say, "I saw it with a telescope," because a telescope's a good thing to see girls with. Yeah? Well, in this case.
So the more famous thing is I shot an elephant in my pajamas, right? By Groucho Marx.
No, that's not more famous. I'm sorry. You're wrong.
Okay.
Okay. I came to the conclusion that the system really need to understand semantics to get PP attachment right. So when you want to parse, sometimes it's ambiguous when you parse sentences. So any sort of grammatical solution to that's not going to work. So you need to have an understanding of words to do that. So I knew about this cell assembly stuff, which is neural stuff. So the way we represent concepts in our heads are with cell assemblies, right? So our semantics are based on cell assemblies. So I knew about this stuff, and I said, I'll just take some of that stuff, whack it in, right, and improve my parser. So it took me about 20 years to do that. It took 15 years to do that. I finally got it in, and it worked. Yeah. So I got the best PP attachment resolution algorithm, and it's in neurons. It's not much better than my PP attachment resolution algorithm, which is just statistical, but there you go. So let's see. Was that Middlesex? No, so I was at Sheffield, and after Sheffield I came here. Yeah, I've been here since 1998. No, really, yeah. Since 1998, yeah. I used to have an office in this building. I used to be here when the atrium was a circle driveway. Yeah, I remember driving in and walking out right there at the front door. Yeah? This used to be lecture theater 2. There was a door back there. You can see where it was. It's right at the top of the stairs. I haven't changed the stairs. Okay, so that's me. You guys, you don't have any questions about me, do you? No? Good. That's cool. I don't have questions about me. Shoot.
Considering you were part of making PB, what are your stances on it now?
What? You mean like it's an entirely competent language that works just as well as any other language? Or?
Yeah.
There we go. I'm sort of with languages, right? So Java, Visual Basic, Lisp, Prolog, they're all sort of the same, right? So Java's got a few more things. VB's actually got a lot of stuff built up around it, which makes it sort of nice and easy, but they're all quite the same. They're just programming languages. The one the guy was giving a talk on, the F#, that was weird. We had a talk last Friday about this guy who's using a bizarre language. But, yeah, it's just weird. Once you get used to him, it doesn't really matter. Unless you're doing something specialized. Neurons are a programming language, by the way. Right? So what my research is on right now, mostly, is on neurons. Right? So I'm using standard models as part of the Human Brain Project. I have my own neural model. So lots of standard neural models. Right? So leak, integrate, and fire models by Brett and Gerstner. Right? And you can download them and use them if you're quasi-interested. The good ones are Hodgkin-Huxley models, because they're compartmental, they break it down. My model is a fatiguing, leaky, integrate, and fire model. It's a relatively accurate model of biological neurons, but they're more accurate models. Right? One of the big things is the cell assembly. So cell assembly is a bunch of neurons that represent a concept. They work in my models, but there's lots of evidence that it works that way in the brain, too. So I have a concept for a cup, right? When I'm thinking about cup, those neurons are firing, right? When you see the cup, they fire. Now they're still firing because you have short-term memory, right? So while, you guys know what neurons do? Xiaochen, do you know what neurons do? Yeah, you do. Okay. So neurons fire, right? They collect activity, right, from other neurons, or they can be directly stimulated from the environment, but that's just like your eye or your ear, right? Right? And if they collect enough activation, they fire, and they send activation to other neurons. Yeah? That's the way neurons work. You learn by changing the weights of the connections, right? Or maybe making new neurons or new connections, or You also learn by having those connections die or the neurons die. It's a different form of learning. That's all the learning we do. When the neurons are firing, all the neurons in your brain, most of the neurons in your brain, fire about once a second. So even the ones you're not using, they're fired once a second. When that thing about you only use 10% of your brain, you don't even use 10% of your brain. Yeah? At any one time, it's, well, what's active neuron? So you're using 1,000th of your brain. If you had all 10% of your neurons fire, or 10% of your neurons firing at any given millisecond, you would go into an epileptic fit, just like that. Yeah, that's what an epileptic fit is. You have 280 neurons firing, right, and your body starts to seize. So where am I at? Neurons, right? So when you've got your concept for cup active, those neurons are firing at an elevated rate, right? And when you see them, they're directly stimulated by the environment. They fire. That becomes active. It's called cell assembly ignition, right? And then they continue to fire. That's short-term memory. So what we've just gone from is from neurons, biology, to psychology, short-term memory. Long-term memory is the formation of those things. So formation of a cell assembly. You formed your cell assembly for cup a long time ago. You probably just formed your cell assembly for Chris's cup. Chris's cup is probably not going to remain in your memory for any length of time. Yeah, you might have it tomorrow morning, probably not next week. There's questions about long-term memory and how they last. Where am I at? God, am I still having this? So I've been working on this here since I came here, right? So I've been working on the cell assembly stuff. We can learn it. So we have standard categorization tasks that we use to learn this. Still, there are problems with the formation and duration of persistence. So how long does your short-term memory persist? I can get my neurons, my cell assemblies to persist the right amount of time, but they don't sort of naturally emerge psychologically. And I need to fix that up. So that's one of my current problems. We've used cell assemblies to create simple cell assembly robots. So I do have a little, you guys have those little Murdo robots, right? So I have my neurons driving a Murdo robot. We wrote a paper on that, didn't we? Yeah. But I've also got virtual robots. So I've got an agent based all on neurons that views the environment, takes some commands from you in natural language, because I do natural language. Remembers where it's been, not very complex memory, travels around the space, bumps into things, and comes back. Right? That's the complexity of my neural agents. Yeah? That's what I'm doing in the Human Brain Project mostly. They respond, Jennifer. And they learn simple things. Learning in this context involves Hebbian learning rules. Right? So Don Hebb came up with the idea of cell assemblies in 1949. And the idea is also relates to learning, synaptic learning rules. So you might have heard of the Hebbian learning rule. Probably not, but maybe. Right? So if a neuron tends to activate another neuron, the connection between them will strengthen. That's the Hebbian learning rule, right? And that's the way, he didn't know that biologically it worked that way, because their biology wasn't that good, but he seemed to think it did, right? He came up with it, and that, if you follow it sort of logically through, you get your cell assemblies, right? So he came up with that rule, and there's lots of biology that shows that that happens now, because we've learned a lot in the last 65 years. Yeah? I got my own Hebbian learning rule. I have a compensatory learning rule, which limits the amount of weight leaving a particular neuron or entering a particular neuron. Which is nice. I'm quite happy with that. We use these systems to learn categories. The performance of the standard machine learning task is categorization. You want to learn categories. I'm making the guys do it in my third-year AI class right now. So they're learning digits. So there's pictures of digits, and they want to categorize other pictures of digits as, you know, 0, 1, 2, 3, or 4. Yeah. Yeah. So that's a standard task. Lots of different standard machine learning algorithms from that. I haven't actually done the digits task with my neurons, right? But we've done other tasks. So we can do categorization with it. If you guys want to do a thesis or on digit categorization with my neurons, we can do that. Yeah? Some really interesting thing with deep belief nets. We might be able to fork the deep belief nets and stuff, but you guys probably aren't there yet. Maybe for a thesis. The paper I just submitted on Monday, right, is on spiking half cognitive model for classification. So I'm interested in cognitive models. So I'm interested in models of how people think. So one of the questions is, how do people learn categories? So I've got a neural model of how people learn categories. It's a half model because it doesn't work the full way, right? It doesn't do a supervised bit.
Maybe you can answer this question, because I'm not an expert in the field at all.
you've got lots of different ways of setting up neural nets, and I suppose some of them are very, very close to what humans have, and then on the other end of the spectrum there are sort of ones that have some other kind of intrinsic structure that works well in situations, and you're working sort of over towards the side of that that's close to humans, that's close to the biological model.
That's kind of you, if anything. Okay, so when you guys think about when you hear about neural nets, and the typical young computer scientist hears about neural nets, they get multi-layer perceptrons. Now, multi-layer perceptrons have a layer of input, hidden layer, and there's connections this way, but no connections this way. So no connections in the layer. The brain doesn't work like that, right? There's no layering in the brain, or there is layering in the brain, but it's not like that, right? And there's all kinds of sparse connectivity, right? So my connectivity is a little bit different. So it's, as Barney points out kindly, right? Mine's a bit more biologically realistic, right? In the Human Brain Project, part of the Human Brain Project, and other modern neurophysiology, they're trying to map that. They're trying to say how the brain is connected, right? So there are lots of simulations where the connections are relatively accurate. Okay, now you can set the connections, that's no problem. The real question is, how do you learn them? Because your brain wasn't engineered, right? All these neurons and synapses grew in response to the environment and, well, in response to the environment. Yeah.
And how do you know these things are accurate, Chris? What is the kind of verification?
My stuff or the biology?
In general. I mean,
so in the biology, you can look, right? You can actually take out, well, first of all, you can look at animal models. So it's pretty easy to crack open a mouse's brain and look. And you can see, you don't need an electron microscope even to see synapses, right? They did Golgi stains in the 19th century on it, right? So they had an idea about how that all connected, right? With, you can also look at behaving animals. So you can crack their brain open, right? Stick an electrode in, see what happens when you turn a neuron on, or see what happens and measure the properties of it. Now, it's not very easy to do that with people. Or it's easy to do that with people, but people don't like it, right? I don't want to have electrodes stuck in my head. There's some work with that, because you have people with epilepsy, right? And they'll go in and crack their brain open and look. So you can do that, but it's hard, right? So if you want to see how neurons are behaving, actual neurons behaving, it's difficult with behaving people. Macaques, monkeys, it's easy, right? Or relatively easy, right? So you have other types of imaging, right? So there's an imaging with fMRI, right? What fMRI does, brain scan on, it's pretty good time, but you don't get to see the neurons firing. It's say, this area of your brain, this 1 cubic millimeter, is getting extra blood flow. So you can say this area of the brain is involved in a memory task, right? Or a speech task, right? And there's a lot of work with that type of stuff. Yeah? Okay. Does that answer the question, Kyle?
Yeah.
Yeah. And by the way, I don't really know, right? I'm a computer scientist. I'm not a biologist. I'm not checking biology.
No.
Right? It'd be interesting to do it. It'd be interesting to work with some people at UCL and go down and stick some electrodes in mice brains, but I'm not doing it.
So in that sense, is a verification method with maybe some quotes around it is in the epiphenomenal effects of a neural network, seeing what that type of structure is able to do and see how much that is similar or dissimilar from a typical intelligent.
Right, so the Human Brain Project does this, right? So I have a little grant in the Human Brain Project. Human Brain Project is a €1 billion project, right? There are other people who have much bigger grants than me, right? And so what they'll do is they'll take areas of cortex, big areas of cortex, and they'll try to mimic them precisely, right? And they'll see if they're getting the right behavior that it does what measurable things are. So they're trying to be as accurate as possible, yeah? So there is lots of stuff about the neural net actually doing what a brain does. But in this case, it's not doing a cognitive task, right? It's not parsing language. It's not walking around an environment. It's just echoing the performance at a coarse level. So one of the criticisms of the Human Brain Project is by Jeff Hinton. Jeff Hinton's big in deep belief nets, big in artificial intelligence, and neural nets in particular. He's kind of at UCL, but he's mostly at the University of Toronto. Right? His criticism of it is if you can build a complete model of the human brain, so simulated model of the brain, all 100 billion neurons, hook it up to a virtual environment, you have no idea how it's going to learn. You can set the weights, but you can't learn the weights. That's his criticism of it. I think actually this is one of the things that we are addressing. Yeah? It's a hard problem, as you'd expect. Okay, so that's my human brain project answering the question forward. I'm just going to go back a little bit.
Maybe there's some sort of quantum kind of thing when you actually try to find out how it's working, you're actually destroying the way it's working or
Maybe,
something.
but I doubt it.
No?
No, because, it's just, the biology is, a neuron fires, it sends electrical signal down its axons, and there's a chemical synapse across. This isn't, they're relatively discrete things. They're really quite far apart. There's not communication at that level. I think we've actually left quantum effects. Now, I'm not saying quantum effects don't matter in lots of things. I don't think they have much
No, I'm
effect
not
in the
talking
brain.
about quantum effects, but just sort of interfering by observing. Maybe you're changing things that you're trying to
No,
observe.
I get it.
Yeah,
Right? So if
okay.
I'm sticking an electrode in a mouse's brain,
Yeah,
is that
maybe
changing
you're-
the mouse's behavior? Well, probably.
Yeah.
Stuck an electrode in his brain.
Yeah.
But not that much,
Okay.
right? Because people in mice are pretty robust. They seem to behave just like other non-electrode embedded mice. Yeah.
You're saying that the mouse is indifferent to having an electrode stuck in its brain.
I'm saying he's surprisingly indifferent.
Okay.
Yeah? Okay, so most of the coding for my model is in Java, right? So I write my model, my flip thing in Java. It sits up on, I can just follow you a couple links here and you can download it and run it if you want. I make the guys in the third year use my model. Yeah? I don't make them use it very much because that's not fair. Yeah, but if you want to, you can, right? So it's an extensible thing. So Java, program in Java. Yeah? Oh, we also have neurocognitive models for a learning and two-choice task. And my favorite thing is I got the best neurocognitive model of natural language parsing, right? Which fits in with the PP attachment stuff. Okay. So the Human Brain Project, for the last couple of years, I've had some funding from the HBP. It's a $1 billion project, just did that. The project is developing several platforms for use in and outside the project. So scientists such as yourselves can use the platforms, right? In particular, one of the things I work with is the neuromorphic platform. So they have not standard chips, but neuromorphic chips. So Spinnaker is an example of it, right? So you want to simulate a lot of neurons on a chip. I got a board in my office with 48 Spinnaker chips. Each chip has 16 processors, ARM processors, and you can simulate about 2 million neurons in real time on that, right? In Manchester, where they made it, they're plugging lots of them together so they can simulate a couple billion neurons in real time on it, yeah? Which isn't the full brain, but it's a lot bigger than it's 2 rat brains, right? If you can simulate a rat's brain in real time, if you can simulate a rat, you're doing pretty well, because rats are really clever, yeah? As you might know if you ever had a rat infestation and tried to get rid of them. Yeah. So you can hit that. So you can hit their things on the internet. So you can download code to it, run it there, and have it come back. Right? There's some other platforms. There's a neurorobotics platform which I'm trying to look at because I've got a virtual environment of my own. I want to use theirs. Right? The idea, it's a 10-year project. It's 2.5 years in. The idea is they'll have a virtual robot which you can use with a high-performance computer platform. So another platform is the high-performance computer platform. So these chips, these neuromorphic chips, are cool for doing robots. But if you want to have a really accurate model, you want to use a compartmental model. You can make them as accurate as you want, each neuron. Right? So this is what they're doing when they're modeling relatively big areas of cortex. And they're not doing it in real time. Right? So it takes a long time to run the model with 1 billion neurons. Right? If you have a robot, that's a problem. Right? Because you want to be running in real time with a robot, which is good for neuromorphic stuff. If you've got a virtual environment, you can slow your virtual environment down. So the high-performance computing guys want to have a virtual environment where their virtual 100 billion neuron human walks around in the environment, right, and does stuff. That's the idea at end of year 10. Right? The virtual environment can be converted to a real environment. So you can have a robot simulate that in the virtual environment, the physics and everything. And the real robot should do what the virtual environment, what the virtual robot does. So that's something that's coming up. So I'm working on that right now. So high-performance computing platform, you can also use the high-performance computing platform. So you can log in, you have to get a password, right? But they're supposed to give them out, right? Log in and send your neural simulation to high-performance computing platform and simulate a lot of neurons in really fast time. So those are the computer platforms. neuromorphic platform, robotics platform, high-performance computing platform, but it's the Human Brain Project. There's also science behind it, right? There's also neurobiology behind it. So they have several databases, platforms, for sharing that data. It's one of the big problems of it is, you're a neuroscientist, you collect some data, how can he verify what you've done? Well, you put the data up, I can use it and drill through it. So they're trying to align that stuff too. We're currently concentrating for the neuromorphic stuff. We, people around here, are currently focusing on 2 neuromorphic platforms. Spinnaker platform, which I told you about, right? Those run on ARM chips, right? And they're discrete. And you can program the neural models, you can program the learning models on them. The Huyck chip is totally cool, right? They're behind. They're not nearly as advanced as the Spinnaker guys. The software is really weak. But it's on the model, right? So the ARM chips, they're just processors. They're on your phone, right? They're in phones, right? And they're discrete. They're von Neumann, right? The Huyck chips aren't, right? They're continuously valued stuff. It depends on the way the silicon's laid down. Totally neat stuff. It happens really fast. You can do the learning stuff on it. I'm really looking forward to getting those things working. We're also spending a lot of time developing neural and synaptic models for the core, nest, and Spinnaker systems. The way these things work is you lay down a topology in Python, right? Python has some libraries that are associated with it called the Python Neural Net Simulator. So you lay out the topology. That is the way your neurons, right, are connected to other neurons. Yeah? You lay that out in Python. And then you send it to a neural simulator. Right? So one neural simulator is Nest. It's just a simulator you can use, right? Standard stuff. There's another one called Neuron. That's been around for 20, 25 years. There's another one called Brian, right? You can take the same topology and send it to each of them, and you should get the same behavior, but you don't. Right? And you can vary your neural model and stuff. Right? Similarly, you can take that middleware and ship it off to Spinnaker and run it on a neuromorphic platform. And it should do the same thing, but it doesn't. Right? And you can ship it off to Huyck and have it do the same thing. There's some variance there. So how do these things differ is an open question. So, what I'm doing with the Human Brain Platform, or Human Brain Project, is I'm programming in Python. Right? So I'm writing Python code to interact with these simulators. In addition to that, I'm writing C code for the neural models on Spinnaker. I'm writing C++ code for the neural models in Nest. I haven't written the neural models in Huyck yet. I'm not sure if I'm ever going to be able to, but we'll see. So you got to program in whatever you got to program in. So the question before about what do you think about Visual Basic? If they had neural models in Visual Basic and I had to program, that would be fine. Yeah, I wouldn't mind. I'd be surprised, but I wouldn't mind. Because, you know, Microsoft is the real world, right? And academia isn't. Right? So in there you want to use Lisp or F# or something like that. Or Python, which seems to be the new hot.
F# is Microsoft stuff.
Oh, there we go. It's Microsoft. No wonder it's a mess. No wonder it's a mess. The guy said he used to go across the street. So this guy came up and gave a talk last week. He was at Cambridge, right?
Yeah, yeah.
And he said the guy used to come from Microsoft Research for the talk, which was across the road from Cambridge. When I worked at Microsoft, there was no Microsoft Research. It was just we programmed. I remember when they formed it. How are we doing for time? My glasses. 7:30. Yeah? No, it's 7:37. They just. How much time I got?
6:37.
That clock's probably wrong.
How much time?
Is it?
Until
6:37.
20 minutes.
Yeah.
So natural language processing, probably more industrially applicable right now than neural nets. Than biological neural nets is natural language processing, right? So I got my PhD in natural language processing. At the time we worked on text extraction systems. What text extraction systems do is they read through documents and give you a template of what they mean. Yeah. When I first came to the UK, I worked at the University of Sheffield and worked on the general architecture for text engineering. You can download Gate, that's general, and with it comes a system that does text extraction. Okay, it does the first bit of text extraction, right? It's not that hard. I got a way to download it, right? Got some slides for that. I've also done some work on information retrieval and dialogue analysis. Does anyone know what information retrieval is? When you Google something, that's information retrieval, right? Because you're retrieving information by searching, right? There's lots of other information retrieval. You can have a much more focused thing than Google, right? So I did some work on that. In particular, I did some work on cross-linguistic information retrieval. Have a query in English, retrieve documents in this case, Portuguese or vice versa. Dialogue analysis? Oh, my best system is a neurocognitive model of NLP, which I talked about. In the real world, we use NLP quite frequently. There are machine translation systems. Anyone tried that? Anyone tried to translate a French document to an English document? Yeah, that's machine translation. Right? Everyone done spell checking?
Yeah.
Oh, gosh. In the back. Sir, have you done spell checking? Yeah? Have you done spell checking? Yes, there you go. Right? So spell checking, that's natural language processing. It's pretty simple natural language processing. There are conversational agents, right? So you talk to the machine. You can do it in voice or you can do it with text, right? Or you can do it by pressing 1 and 3 on your phone, right? That's a really simple conversational agent. These are things that I have people do in labs. It's easy to make a conversational agent. Turns out that the more sophisticated it is, the more difficult it is, as you expect. Sort of goes up exponentially in difficulty. There's speech recognition. All these problems are open and require software developers to build new domain-specific systems. You guys want a job? Sorry, spell checking is not really open, right? But that one's pretty much solved, right? The other ones, you want a job? You want to be interested in building conversational agents? Does that seem like a fun job? Yeah? Well, it depends what the conversational agent is about, right? Okay, how about speech recognition? You guys interested in that problem? So you guys have a phone that you talk to and it does it correctly?
Yeah, it's actually pretty good now.
Any problems with it?
No, it's leaving.
Never have problems with it? Yeah, what if you're in a noisy room?
Yes.
Yeah. Do you have problems talking to someone in a noisy room? When you talk to someone, do you have problems? Do you understand someone in a noisy room? Yeah?
Depends how noisy it is.
It has to be pretty noisy before you can't understand someone. And then you can do that thing where you just look at their mouth and see what they're saying, right? Especially if it's pretty, yeah, okay. A pretty person, yeah? Okay, so speech recognition, open problem. There's the new technique right now. So for speech recognition, cool, right? For 40 years, the best solution was hidden Markov models, right? And in the last 5 years, deep belief nets. So deep nets are the new way of solving it, right? So Siri's got deep belief nets, not you. Oh. Yeah? So new technology, we're figuring out deep belief nets. They're kind of like binaural stuff, right? But it's a bit different too. Yeah? Hinton, who I mentioned before, who criticized the Human Brain Project, he's the guy who came up with deep belief nets in particular. But deep nets, big technology, right? In machine learning. So one of the, next slide. Text extraction systems. Okay, other AI. There are lots of jobs in AI. Big field right now is machine learning. The big bit of big data. Right? You guys have heard of big data? You haven't heard of big data, right? Oh Lord. Okay. You know about the Google robot car, right? Self-driving car. How much information does that go through? A lot, right? Do you know about SETI, Search for Extraterrestrial Intelligence? Yeah? Right? They get lots and lots of radio waves. They have to go through and analyze them. Right? So you've got huge data sets that you're trying to mine. Now that's not a particularly big one. Right? What about Google itself? What does it do? Just the search engine. Just Google. Right? Just the way they make their money. They only really make money from the search engine, right? Right? So that Fortune 500, Fortune 100 company, biggest companies in the world, perhaps the biggest company in the world, based entirely on a search engine. How do they get the information they need? Data mining.
They plant a seed, basically.
They do what?
Basically, they plant a seed, like let's say.
They plant a seed?
Yeah, like on LinkedIn, on BBC website. Let's say, how do I explain this?
By the way, the paper's online that the company's based on. So
Okay.
I mean, they've had the paper out 15 years ago. So, but you know,
Yeah.
they troll lots and lots of clicks,
Yeah.
right? They get first of all the information they can, right? So all the web pages they can, right? And then they look at what searches work, right? They do the keyword search, right? They see what other pages reference it. It's a big machine learning problem. They seem to be using deep belief nets now for it, right? So if you could build something that was better than Google, would you make a fortune? Search engine that was better? Well, you'd be in with a shot, yeah, because they do have a bit of market dominance, right? I'm sure they put 1,000 engineers trying to figure out how you did it and rip off your technology as soon as they possibly could.
There's a new search engine that's coming up competing with Google right now.
Which one?
It's quite a small one. It's, I can't remember
Cool. Yeah, no, so there's no reason you can't come up with a better search engine, right? But Google does have a pretty big lead. Yeah. Well, they also say, with Bing, right? And Microsoft's been competing with them forever, right? The most frequent query on Bing is Google.
Well, this university forces us to use Bing, right, on these computers. Yep.
I don't think the university forces you. I think the university can't be
How do
bothered
I
to change it.
How do I change my default search engine to Google? Is the most searched thing on Bing? Yeah.
No, it's not.
Quite interesting. It's like this Shazam.
Shazam?
Yeah.
You mean like the comic book?
No, the
No, okay.
Shazam, the audio recognition.
Oh, so like Siri, yeah? So speech recognition.
Yeah, but that kind of like recognizes item, whatever track or music or whatever the thing was going on.
Oh, that kind of recognition.
So that Siri does now. So you can just use your.
So why is, so it's an interesting question. You got soundtrack recognition. Why is that a more difficult problem than speech recognition?
Because again, you got like it's because of its accuracy. Every time we're treating information.
It's too accurate though, the soundtrack, because if you give it two pieces that are the same piece but rendered by two different people, it can't see that they're the same piece. It's too accurate, that sound recognition. Sound
still brings the right one every time.
Sorry?
You've got like let's say old track and new track. Some old tracks are rejuvenated and brought up in like new music, whatever it is. But it always brings out whatever is playing.
No, but Barney's point is like in classical music, for example,
Yeah.
if it's an orchestra, a different orchestra playing.
It's too perfect.
Yeah.
It's just doing local pattern matching. Actually, that's the problem. It doesn't hear it like a human hears it.
But it's got tons of millions of
Yeah, fortunately, it's got so many. But then if you play one that it doesn't have, like if I play a piano, if I sit at a piano and play something to it, will it understand it? Sorry, Chris.
No, there's a generalization question, right? So I know there's software that does this. I'm not sure if this is the thing you're referring to, where I hum something, and it gets the real tune from it, not my version of it, right? It goes out and finds the Rolling Stones. It's doing a much more general search.
Oh, that's very clever.
No, it's not that. It's not even more clever, right? It's just a more broader. It's more. It's a less restricted search. If you want to do an exact pattern match, and you got lots of data. The question is, how do you do it fast, right? Because there's a lot of things to troll through, right? So you probably need to do some hashing function, right? That breaks it down pretty quickly, right? If you want to do the more general search, then you have to have a more broad search engine, as it were, right? It's a relatively straightforward thing to do. These are machine learning problems, right? So the big thing in computer science right now is really good computer scientists come out of undergraduate, start their own company. That's the way you get rich. When I left Microsoft, someone wisely said, the way you get rich is making your own company. Never got around to it, I came here. Right? But my buddies who stayed at Microsoft are quite well off. Right? So I dropped the ball there, but probably just because I didn't start my own company. Right? So there are all kinds of cool applications to make.